Thank you, Dr. Chu. It's a great pleasure to be here today and have the opportunity to present my work. Thanks for the introduction. I'm Stareh Kazemi, a fourth-year PhD in Industrial and Systems Engineering at the University of Buffalo. Today, I want to talk to you about this project that I did for providing a privacy-preserving method for human activity recognition. And I more specifically use the federated deep learning approach for this purpose, thanks to all my colleagues and co-advisors who helped me throughout this project. So first, I'm going to introduce the problem. I'll go through the experiment and data collection. Then we'll review the state of the art and find the gap in the current literature. And then I'm going to introduce the proposed framework and finally present the case study and results and later summarize and mention the future work. So why is this important? So my main goal in this project was to be able to provide a monitoring model that can be helpful in providing a safer environment for electrical line workers, but in generally more for like all kinds of workers in occupational settings. But to do so, we first need to understand what is the sorry for that. We need to understand what is the work domain characteristics to be able to come up with the right risk assessment factors. So if the work is specifically requiring heavy loads or is performed at a height, it requires a different set of actions compared to easier tasks. Once we understand the type of work and what it entails, we'll understand, we can like collect the related data and understand more information about the task itself. For example, what is the type of task they are doing, or for how long, or for how many repetitions. And once we gather this data, we can then proceed to next steps for a better management of the system, for better risk assessment, and provide more evaluations on performance of the workers and provide some more trainings in this regard. This is a conceptual framework that our research group provided in an earlier study, which goes through a 5-step procedure for ergonomic risk assessment for occupational settings. As you can see, the first step is defining the objective, and then later we proceed to collect the related data and pre-process them to then enter the fourth and most important part, which is the task analysis. In this study, my main focus is on section 4A, which is segmentation and task identification, because it's the initial step towards understanding what's going on in the work environment and be able to provide real-time feedback and prevent any injuries. But why is it important to work on the a specific area of electrical line workers? Because they currently have one of the top 10 most dangerous jobs in America, with 21 deaths per 100,000 workers. So by understanding the type of activity they are doing at a real-time basis, we will be able to provide a real-time safety monitoring for them. And in order to do so, we are using wearable sensors. But it comes with so many different challenges. For example, the data that is collected in this way is very high dimensional, and also most of the workers don't like the idea of having a smart sensor attached to them all the time and knowing that they are being monitored constantly. So we need to come up with a method that improves this and also ensures them that their privacy is protected. So our approach is to ensure that by providing a federated learning approach. In order to collect data for our experiments, we did a lab experiment in one of the halls at our university, where 37 mostly students were hired to do a set of exercises and tasks that were very similar to the tasks of electrical line workers. As you can see here, they went through like some general work tasks and more specialized work tasks. For example, working on an electrical panel for different durations of time or repetitions. And while they were doing so, they had an empathic IE4 wristband attached to their dominant wrist, which collected their triaxial acceleration data that were used later in our study. Before proceeding to the proposed framework, I just want to quickly overview the studies that have been done in this regard. As you can see, these are the most recent studies in human activity recognition area, which have used sensors, specifically the acceleration sensors. But as you can see, most of them have focused on a centralized model. And by that, I mean the models that do not provide any privacy preservation because they collect all the data and store them in one central server. But you can see in records 6, 8, and 9 that there are some papers that have focused on federated approaches, but unfortunately, their main case study was related to daily life activities. So they are not focusing on specialized activities of workers in occupational settings, which is why we have addressed in this case. Our proposed framework can be shown in this figure. As you can see in phase 1, we performed data collection, we recorded people while they were performing those different tasks and annotated their recordings that were later used in our study, and we created a database on our clouds. Then in phase 2, we pre-processed this data. As you know, like these signals are very high dimensional, and therefore we first segmented them into some non-overlapping 10-second windows, and then extracted some time frequency or wavelet features out of them, which were then added as an inputs into our model. And I'm going to tell you a bit more about the details of the model. But finally, the model was compared to the other traditional, more centralized models so that we could compare the different approaches. And accuracy measurements were taken to make these comparisons. So here you can see general introduction to the federated averaging method. On the left side, you can see a worker that is like pushing the cart and is wearing a wearable sensor. So in traditional models or centralized models, the idea was that the data from all these different sensors were located in one server, and that exposed them to like the risk of no privacy at all. So what federated learning does is that the data itself is located at the wearable sensors, or we call them edge devices. So in this way, we do not move any personal data to any server. But instead, there are two types of models that get trained. One on the edge devices, which are the smart sensors, and one on the global model, which is in the server. And only the parameters get updated at each iteration and get broadcasted between the edge devices and the server, which is, in this case, we call these types of models decentralized because the actual data stays in the sensor, but instead the parameters are transferred between the server and the edge devices. So this way we will ensure that the privacy is preserved. Next, I want to show you a general overview of different sensor signals and different activities. As you can see, the shape of these signals is very different from one activity to another. But with one exception, like sitting and standing, you can see that their signals are very similar, which brings me to my second point. As you see, we have focused on all three different axes from acceleration, and we did not turn these into the magnitude because we exactly wanted to be able to differentiate between the standing and sitting. If we had turned into the magnitude of the signals, we wouldn't have been able to do so. And next, you can see the idea behind the feature extraction. So we only extracted some 10-second non-overlapping windows, and out of those, we extracted these wavelet features that were later used as inputs to our model. We had a 80-20 split for training, meaning that 80% of subjects were used in the training set and 20% in the test set. We used 4 different centralized models to be compared to our federated approach. The traditional ones are support vector machine, K nearest neighbor, and random forest, and the LSTM long short term memory. And the federated one was the LSTM along with the federated approach. And we did hyperparameter tuning and tenfold cross-validation to do so on a grid search. Here you can see the overall result of our method. In the first table, in the upper table, you can see the traditional methods in white, but our method in gray. So you can see that they all have a really good performance with an accuracy of above 90%, which is really considered to be a high accuracy in human activity recognition. But we see that we are losing about 3 to 7% of accuracy at the expense of preserving this privacy, which is still very low. And I should also mention that its runtime is very close to real time, so it's another bonus of using this federated approach. In the bottom table, what I wanted to emphasize on was the difference in activity between different participants, which brings me to another point, which is the heterogeneity among participants, which needs to be taken into account in the future model. So to summarize, we saw that the privacy preservation can be done with just the expense of losing 3 to 7% accuracy using input from only one single variable sensor. And in the future, this is an ongoing work. I'm currently working on incorporating clustering into the model so that I can tackle that issue of heterogeneity. Thank you so much for listening to my presentation. I also want to acknowledge the funding that I received from the CDC, NIOSH, and ERC program. Thank you so much for this opportunity. These are my references. And I'm open to any questions. Please scan this barcode to stay in touch, and I look forward to any questions you might have. Thank you.